And just as you might expect, a slightly more complicated, bless you, model of computation requires a little bit more complexity in our definition. So DFAs, NFAs had 5 tuple formal definitions. PDAs, we need 6. And Q is the set of states. So let's just right next to it do in our example what each of these will be. So for our example, Q is a set of states Q0, Q1, Q2, Q3. Sigma, our input alphabet, has just zeros and ones. The stack alphabet is the collection of symbols that might show up on our stack. Okay? And in our example, what were the symbols that could have shown up in the stack? Yeah, go for it. 0, 1, and $. Cool. So if we go back here, we're looking for symbols that show up in that blue part of the labels. So epsilon's not a symbol, it's just a label. It can't show up in the stack. But $sign shows up, 0 shows up. And if we write additional symbols in our stack alphabet, it doesn't hurt us. We're not going to use them. But we don't happen to actually use any ones on our stack in this machine. We're using the zeros to record the number of zeros that we saw at the beginning. And when we read a 1, we're not pushing that 1 onto the stack. We're popping a 0 off the stack in order to do the matching. So while it's not wrong to say that the alphabet could be bigger than it is, we actually don't need that 1. Okay. Cool. All right, I'm going to skip delta for a second, because that's always long. Let's do the start state. And that one, familiar. We're looking for the triangle in our diagram, so that's Q0. And it's a single state in our set of states. F is our set of accept states. We have 2, so we write the set whose 2 elements are Q0 and Q3. Okay. Now the big difference, other than the fact that we had this new parameter, the stack alphabet, is our transition function has to work a lot harder. So remember, the transitions now tell us what we're going to do based on our current state, any input we'd like to read from the input string, or if we want to ignore for now, so that's where the epsilon subscript is coming from. And then, bless you, we might care about what's happening in the stack before we follow an arrow. And then we may have a couple of choices of where to go next. And so that's where that power set symbol is coming from. And we have to specify the next state as well as whether and what to push onto the stack. Okay. Bless you. And so let's do an input-output table. And our input is going to be an element of that Cartesian product, the threefold Cartesian product. So it's going to have a state. It's going to have either a character from the input alphabet or the epsilon label. And it's going to have either a character from the stack alphabet that we want to pop or the epsilon label that says we're not going to pop anything. Okay. So this is in Q cross sigma, make it bigger by adding the new label, and cross gamma, make it bigger. What we can do instead of listing out all, a bunch, many, is just figure out which arrows we need. So there's 1, 2, 3, 4, 5 arrows in the picture. We can have 5 rows, which we specify, and anything else will have an output of the empty set in the transition function. The output, remember, is telling us about the set of possible arrows we might follow. So it's in the power set of which state we might land in and what symbol we might push onto the stack. So to represent that first arrow that goes, bless you, from Q0 to Q1, then we've got our input is Q0, and we're not reading input. We're not popping anything from the stack. And the output in that case, we've only got one arrow to follow. So it's a set with one element, and that element is a pair. Q1 is the state we go into, and we push in the $ symbol. The self loop originates at Q1, requires us to read a 0 from the alphabet. We don't pop anything, and we must go back to Q1, and we push a 0 in. Okay. And I'll leave you to fill in the remaining 3 arrows.